Gotta get my coffee too. I'm trying to maximize my productivity while minimizing my caffeine intake so I don't jitter while I do this video. Good morning, good afternoon, good evening, good night, good whatever time it is where you are. Welcome to today's Math Minute. I want to do something on linear optimization, also known as linear programming. So something I try to emphasize to my students a lot is I don't care at all whether or not the stuff that I teach in class is practical. So that question that you sometimes get from 7th graders, 8th graders, 9th graders, why are we studying this? Why do we have to study this? When are we going to ever use this in our job or in our lives? I don't care. I just think it's cool, and so I teach it. I also get paid to teach it, which is nice, but I would do it even if I didn't get paid. I mean, literally, I am doing this right now, not getting paid by you good people watching this video. However, of all the things that one learns in middle school or high school math, Algebra 1 style math, this is arguably the most useful, the thing that you could conceivably be doing in a job one day. Because linear programming or linear optimization is all about maximizing or minimizing some quantity, optimizing something in the face of constraints. Usually the examples we use are about profit, because that's easiest to think of in terms of course, we want to maximize profit. We want to make the most money possible. These are usually linear inequalities, not linear equations, because that resource, our constraint, we're typically going to have up to so much of something, so much money to buy supplies with, so many supplies in the first place, so much time. But there's going to be some kind of limited quantity, and within that limitation, we will then go about maximizing or minimizing some other quantity. I think it's probably best to jump in with an actual example, and I have one right here of my own devising. A carpenter makes either tables or chairs. He nets $45 profit on every table that he sells and $38 profit on every chair. He works up to 60 hours per week. Each table takes 2 hours to make and requires 6 2/3 board feet of lumber. Each chair takes 3 hours to make and requires 5 board feet of lumber. The carpenter has available 160 board feet of lumber each week. What number of tables and chairs should he plan to make each week in order to maximize his profit? So there are a few things we want to look for every time we do a linear programming question. Number one, what's our objective? In fact, we're going to write what's called an objective equation. This is our goal. This is the thing that we're trying to either maximize or minimize. In this case, it's pretty clearly the profit that we're trying to maximize. And so we are going to write an objective equation determining how we calculate profit. To be able to do that, of course, we need some variables. What do we not know in this situation? We don't know what number of tables and chairs he should plan to make. So let's go ahead and say that X is the number of tables that he's going to make, and Y is the number of chairs. In that case, it's relatively easy for us to then turn that into an objective equation. We are trying to maximize P, profit. Every time we sell a table, one of those X number of tables, we make $45 profit. And so that's going to be 45 times X, whatever that unknown number of tables is that we create. Of course, we also know that the carpenter makes $38 of profit on all of the chairs. Again, we don't know how many chairs. We've called that number of chairs Y, but for whatever that is, we make $38 each time. And so that is our objective. We are trying to maximize profit, and the way we calculate profit is 45X plus 38y. Now notice you would not graph your objective equation. This is a linear equation, but it's not one we can graph because we don't know that quantity p. You could actually imagine graphing this in 3 dimensions, where p is a third variable that depends on the other two quantities, and it would give you a 2-dimensional surface, and you're looking for either a high point or a low point on that surface. But 3-dimensional graphing is not something we typically teach in these 7th, 8th, or 9th grade years, and it's also not super easy to visualize what the relationships are in 3 dimensions. So we're going to need a shortcut in a moment. But we're getting a little ahead of ourselves. We need to know what are some possible x, y pairings. We need to know what is some possible number of tables that we can produce and what is some possible number of chairs that we can produce. Of course, to figure that out, we need to incorporate our constraints. We know that we're limited on the amount of time that it takes to make these objects and in the amount of supplies that it makes. In fact, that's going to be our next step. Let's go ahead and write down those constraints. We have a constraint on our time, and we also have a constraint on our lumber, our board feet of lumber. We're told specifically we have up to 60 hours. So our time inequality is going to be something is less than or equal to 60. Our lumber inequality, we're told that we have a limit of 160 board feet of lumber. And so we're going to have some quantity less than or equal to 160. Now, of course, I said this is a linear inequality. We're going to bring back these variables, x and y, because as we make tables and chairs, we're going to be using up so much of our time and so much of our board feet of lumber. Specifically, for the x number of tables that we create, each one of them takes 2 hours to make. So if we made 10 of them, 2 times 10 would be 20 hours out of our up to 60 hours available. For the chairs, they take 3 hours to make. So that's going to be plus 3y. For the lumber, we have an awful mixed number, so let's go ahead and convert that really quickly. 6 2/3 is the same thing as 20 over 3, and so we have 20/3 board foot of lumber for each one of those x number of tables, and then 5 board feet of lumber for each one of those wide chairs. Now, once we've developed these inequalities, we want to graph these in the coordinate plane. The coordinate plane is by far the best way to visualize the solution set to a system of inequalities. This isn't like a system of equations where the only thing we're interested in is the one point where these two lines intersect. That should be one possible solution, but there are going to be lots of other possible solutions if we don't work up to our full 60 hours, or we don't use up to our full 160 feet of lumber. And of course, if we're graphing these, we can just use a graphing calculator, and I will show you this on a graphing calculator in a moment, but there's something useful we can do before we go to the graphing calculator. I want us to think about the extremes. I want us to think about, what if we only make tables? What happens if we spend all of our time or all of our supplies on the tables? And what if we only make the chairs? What happens if we spend all of our time or all of our lumber just on the chairs? Essentially what we're doing here is finding the intercepts for each one of these linear inequalities. Like, imagine for our time that we spent no time whatsoever on the actual number of chairs. Basically that we built 0 chairs. 3 times 0 is 0. If we only built tables and they take 2 hours each and we have up to 60 hours, how many of the tables can we create? Well, we could solve that very easily by just dividing everything by 2. 60 divided by 2 is 30. And so if we only think about tables and we only think about hours, we could make up to 30 of the tables. That ends up being our x-intercept, 30, 0. If we did the same thing for the chairs, if we completely ignored the tables or presumed we made 0 tables, with just our time constraint, how many chairs could we make? 60 divided by 3 is 20, and so that answer is 0 tables and 20 chairs. Let's do the same thing now with respect to our other constraint. If we only made tables and we use all 160 board feet of lumber. So basically we're going to completely ignore the chair part of that inequality. What could x be here? Well, we would either multiply both sides of this inequality by 3 over 20 or divide by 20/3. That ends up being the same thing. And what we're going to get in that case is 8 times 3 is 24 tables. So there's another x-intercept, 24, 0. And one more time, let's say we make no tables whatsoever. We only make chairs. Since they take 5 board feet of lumber and we have 160 available, divide by 5, divide by 5. And that means we could make up to 32 of the chairs if we're only thinking about the constraint of our supply, the number of board feet of lumber we have available to us. We could now go to our coordinate plane and we could use these various intercepts to create the system of inequalities. So think about just the x-intercepts for a second. With respect to time, we've got 30, 0, which of course is going to be somewhere over here, 30, 0, and then 0, 20, which we'll just say is somewhere up here. Again, we're going to go to a graphing tool in a second. We're just trying to sketch this relationship out, and we want all the solutions under this line. And so that would be this kind of shaded region in here. For our lumber constraint, that x-intercept was a little bit further in here, so 24, 0, somewhere over here, and that y-intercept was a little bit higher, 0, 32. And again, what we want to do is connect the dots. Because in both cases we have up to that constraint, up to so many hours, up to so much lumber, again, we want this shaded region under both of the lines. And so we're going to get this distinctive quadrilateral shape. This is going to happen a lot on these linear programming questions. and it's going to have these 4 corners. Anything in that shaded region is a possible number of table and chairs that we can produce. And obviously, there are going to be lots of possibilities there. So we need something to simplify our work. The great thing about these programming questions is, remember, our objective here was to maximize profit, and the maximizing point or minimizing point, whatever the optimizing point is, always has to be one of these 4 corners. This actually goes back to the 3D graphing thing I was saying earlier. This objective equation, if we did graph it in 3 dimensions, would be a tilted plane. And so at one of the corners, as you tilt that plane in different ways, that corner must be the maximum possible profit for a given x and y ordered pair. Basically, that means when I take this maximizing equation, my objective equation, 45x plus 38y, I only have to plug in those 4 corners to find which one ends up with the largest profit. Whatever the largest profit is with those 4 corners is the optimized solution to the problem. 3 of the corners we already have, because of course we know the least possible number of tables and chairs we make is 0, 0, and we already solved for the 2 intercepts. The only other thing we need is this corner where the 2 linear inequalities, the boundaries themselves, intersected. You could solve that by hand, but at this point I'm going to go ahead and type this into my graphing calculator and let it do the hard work for me. I'm going to use Desmos, but any graphing calculator would do. So again, 2x plus 3y was less than or equal to 60. Oh no, the whole coordinate plane is shaded in. Just zoom out a little bit. Right? We just need the numbers to be a little bit larger. You can see those intercepts we came up with earlier, 0, 20, 30, 0. For the other inequality, we had 6 and 2/3. Remember, mixed numbers are statements of addition, so 6 plus 2/3 x plus 5y is less than or equal to 160. So there you have it. That is that shape I was talking about earlier. Of course, we're going to need another corner over here. It's not really cooperating and letting me select all of those at the same time, but you can see the 0, 20, one of our boundaries. Of course, over here we've got the origin. It's not coming up for me, but it's there. We've got 24, 0, and then the one other point we were concerned with, that corner, which was the intersection between the 2 boundaries. In this case, we can see it's 18, 8. Taking these 4 solutions, I'm going to go back to that objective equation, and I'm going to plug in 0, 20. 24, 0, 0, 0, which is pretty obviously not going to maximize my profit, and then 18, 8, that other corner we just figured out. Each time I am multiplying those tables by the $45 profit per table and the chairs by the $38 profit per chair. And I'm just going to see, as we plug this in, which of these 4 possible profit amounts is the largest, and that will be my optimized solution. In this case, the one that maximizes profit. Starting at the bottom, 45 times 0 plus 38 times 0. Obviously, if we make nothing, we make nothing. We make $0. 38 times 0 is 0 plus 45 times 24. That's 90 times 12. That's $1,080. Pretty good, over $1,000. 45 times 0 plus 38 times 20 is only $760. That makes good sense. Our chairs are less profitable and they take a lot more of our resources, so making a bunch of chairs isn't really a great idea here. And then that intersecting corner, 45 times 18 is going to be 810. 38 times 8, can I do that in my head? I think it's 304. So 304 plus 810 is going to get us 1114. And so there it is. The best way to spend our limited resources of time and lumber would be by making 18 tables and 8 chairs a week, and that's going to net us $1,114 of profit. That is my maximized solution. I'm just going to close out with this. I have another example if you would like to try this out on your own. Linear programming. Again, you need to write inequalities for your constraints, whatever your limitations are. You need to find the solution set of those inequalities by looking at the shaded region that satisfies all of your inequalities. You need to pay special attention to the corners of that region because your optimized solution will always come at one of those corners. And of course, you have to have your objective equation. What is it that we're trying to optimize for? What are we trying to maximize or minimize? That's the equation we plug our corners into, and whatever is the max or min solution for that objective equation is the answer to the question. I'll set up a few inequalities here, but I'm going to let you figure out the rest. A local manufacturer produces personalized plastic beer mugs and champagne glasses. Each case of the mugs yields a profit of $2.50, while each case of champagne glasses yields $2. Right away, I can tell that's going to be related to my objective equation, right? In fact, I could probably write already P, my profit, is $2.50 times the X number of cases of mugs plus $2 times my Y number of cases of champagne glasses. The cups are made by a special machine called a plastic extruder, which takes plastic resin as an input. The manufacturer has 1,800 pounds of plastic resin available on a daily basis. That's a constraint, right? That's a limitation. So when it comes to the supply of resin, we have less than or equal to 1,800 pounds. A case of beer mugs requires 20 pounds of plastic resin to produce, and a case of the champagne glasses requires 12 pounds. So again, I can go ahead and use these variables X and Y. I didn't write them down earlier, but X is the number of cases of mugs that we make, Y is the number of cases of champagne glasses. In this case, we could say 20 times X. That's the 20 pounds of plastic resin for the beer mugs, plus 12 times Y. That's the 12 pounds required for the champagne glasses. Needs to be up to 1,800 pounds. The machine produces about 15 cases of either kind in an hour, so their hourly rates are the same, but the manufacturer only runs the machine 8 hours per day due to electricity costs. And so we're going to call this limitation hours. And what can we say about hours? Actually, I guess I wouldn't really do it in terms of hours. I would actually just do it in terms of cases. If we're making 15 cases of either kind per hour and we run the machine 8 hours a day, that means we're going to make up to 120 total cases. 15 cases per hour times 8 hours per day. 15 times 8 is 120. But again, their rates are themselves the same, so we can simply say X plus Y is going to be less than or equal to 120. Basically, the total number of cases we make is 120, and it's any possible combination of the beer mugs and the champagne glasses that adds up to 120. That is what we're interested in. The rest I leave as an exercise to you. Take these constraints, throw them into Desmos or whatever your favorite graphing calculator is. Look for those corners, those intersection points. Again, what we're typically interested in is an area that's going to look something like this. Ooh, that's terrible. That's going to look something like this, and we're going to look for those corners, look for those intersection points, and figure out, as we plug them into our objective equation, what maximizes or minimizes something. In this case, maximizes profit. Comment down below with any questions you have. What steps did I skip over? What doesn't really make sense? Let me know what you got. How many champagne glasses are you going to produce? How many cases of beer mugs are you going to produce to maximize your profit? And otherwise, I'll see y'all next time.